Hello, everyone. I'm excited to have you here today. It is Percona Live, and my name is Sergey. I'm a group product manager at Percona. Today, I'm going to talk to you about physical backups with Percona Backup for MongoDB. This is the agenda. So maybe not all of you know what Percona Backup for MongoDB is and what it actually provides, what kind of value. So today I'm going to talk a bit about it. So it's going to be a quick overview. We're going to look into the differences on high level between logical and physical backups. Just super quick, like an overview. And then I'm going to talk a bit about our comparison between performance of physical and logical backup in PBM. And the last but not least, this section will take us through physical backups, technical realization, what we did to implement physical backups in PBM. I really hope it's going to be super interesting and enjoyable journey today. So let's begin. Overview, right? So first of all, what you need to know about PBM. I'm going to say PBM today a lot. It is Percona Backup for MongoDB, PBM. First of all, it's 100% open source and free. You can find it on GitHub. There will be links somewhere in the end of this presentation. You can see it. It's a Apache license, so feel free to play with it. It is enterprise ready. What I mean by that is that I know that there are a lot of our customers and other users in community who are using PBM in their production environments, and they're pretty happy with it. So that's why I'm saying it's enterprise ready. Number three there is it is feature rich. And I'll talk about some of these features a bit later on, but what you need to know is that it's fully compatible with major public clouds. Usually what I mean by that is that if you run MongoDB somewhere in a public cloud, you can take your backup and upload it to the storage of your choice in this cloud. Usually it is either some S3 compatible storage like Amazon S3, or it can be MinIO if you run it somewhere on your own premises. It can be Azure Blob Storage, it can be Google Cloud Storage, GCS. So a PBM can upload your backups to this kind of storages. We do support the backup and restoration of regular replica sets and sharded environments. So there are multiple replica sets, they're all sharded. We can support that and maintain consistency. That is crucial for the backup. We do provide the point-in-time recovery, which can help you to minimize recovery time objectives and recovery point objectives. These are very crucial for disaster recovery or even for regular, hey, just spin up the database for me in staging. So you can do it much faster. And we also provide physical backups. Currently, they are in tech preview, and they're going to be GA, I believe, in a month or two, once we finalize all the tests and polish it a bit. But we're going to talk a lot today about physical backups, and I'm pretty excited. And number four here is supported by Percona. I believe it is extremely important for big companies, for enterprises, or for companies who are very careful with their data, that you can be sure that the product that you use is supported by some company or by big community. In our case, it is both. So we're open source, and we have our engineering, our global services team, which are ready to help you to implement and enhance Percona Backup for MongoDB in your environment. Good. So this was just super generic information. Let's see how PBM looks like inside, right? It is the architecture of PBM. So there are three main components that you need to be aware about. First one is PBM agent. PBM agent is just a process that runs on every MongoD node within the cluster or replica set. And this process actually performs the backup and the restore operations. So it's just a daemon running on each and every node in the replica set. When I say replica set, I also mean, for example, configuration server replica set that you have in a sharded cluster. Another component, PBM CLI, command line tool, or command line utility. This is the tool that you interact with as a user, and it interacts with PBM agents running on MongoDB node. A single PBM agent is only involved with one cluster on non-sharded replica set, and the PBM CLI utility can connect to any cluster it has network access to. So it is possible for one user to list and launch backups or restores on many clusters. This actually enables you to run a machine somewhere which would orchestrate the backup and restoration of multiple clusters that you have running somewhere, right? And another important piece is PBM control collections. These are the special collections that we use or used by PBM, and they are stored in your MongoDB cluster. This collection has all the information about the backups that were taken by PBM. And both PBM CLI and PBM agent use these collections to check backup statuses in MongoDB. And we also use these collections for PBM agents to communicate with each other. Because when you take a backup, it's very important that there is a consistent messaging happening across PBM agents so that they know which one is uploading the data and so on, or restoring. Right, so these are the three most important components in PBM that you need to know about. This is the quick comparison because there's this quite a popular question like how PBM is different from mongodump. And I understand that mongodump is pretty cool. I really love it. It's a good utility, mongodump and mongo-restore. But if you compare PBM and mongodump, these are the three key components, right? So, So first one is sharding. MongoDump does not support sharding. This is version 4.2, I think, and PBM does. MongoDump does not have any CLI, which means that if you need to check the status of your backup or list the backups, you need to do it with some other tool or go to the storage directly and figure out where is it and so on. But PBM provides you this information through the CLI. And obviously physical backups, even in PBM, it is in tech preview, but it's going GA soon. So, and MongoDump does not have it. So this is it. Going forward, let's talk about logical versus physical. This is going to be a quick overview. So if we talk about logical backup, what it really is in a nutshell is that you read the data from your database, from in this case, it's MongoDB, and you take this data that you read, you convert it into some binary format, you compress it, you can put it into some archive, and you store it somewhere on some storage, S3 compatible, for example. And then when you do the recovery, what you need to do is you need to get this data in this binary format. You write this data into the database, and write is the critical word here because you really writing this data, you're inserting it back into the data through your database protocol, or like it's similar like executing a command through Mongo shell. And in the process of this recreation of this data or writing this data, you need also to recreate the indexes and synchronize all your nodes. Like imagine you have a replica set with 3 nodes, and you are restoring the backup to one of the nodes. You are writing the data, you're creating indexes, and at the same time, you need to sync the data to other nodes in the same replica set. So this is what's happening, and this, again, super high level overview. What's happening with physical backup? You do not interact with the database here. This is the key difference. You take the files from the disk itself, from your file system. In the case of MongoDB, it is White Tiger files. And again, you store them somewhere on some storage. And during restoration, you just take these files and put them on the disk and start MongoDB. That's it. So you do not interact with the database when you talk about physical backups. So database layer does not take any part in the backup and restore process. Well, it takes, but we'll talk about it a bit later, but it doesn't do any heavy lifting, so it does not consume your resources. It does not slow you down. And when I talk about slowing you down, we did some tests, and we recently wrote a blog post about it. I will give the link to it in the end of this talk. What we did is we created a test setup. We took a MongoDB cluster with 3 node replica set. We spun it up on DigitalOcean. There were 3 machines, 16 gigs of RAM, and 8 CPUs each. So 3 nodes, 3 machines. We decided to upload our backup to DigitalOcean Spaces. And the data that we generated was randomly generated. I think it was MongoGen or something like that. And it's like 1 meg documents. So it's randomly generated data, some rubbish. And the results are the following, right? As you see here, physical backups is in green. Physical backups and restore is in green, and logical is in red, let's say. So, and on the left scale, you have minutes. On the left, on Y scale, you have limits, and on horizontal scale, you have the data. And as you see, for like 20 gigabytes of data, the difference between backup and restore is not significant, right? And even sometimes, no, logical in this case is not faster, but it's a bit slower still, but it's not relevant, right? So for this amount of data, it doesn't matter. When we move to 400 gigabytes, so it was 20, now we talk about 400, we see that backup time is 35 minutes for both logical and physical. So it's similar, it doesn't change. But when we talk about 400 gigabytes and restore, then we see that logical took 156 minutes versus 36 minutes for physical. And it is a significant difference, right? It's 5x in restoration time, which is a lot. And when we talk about 600 gigs, we see this similar situation that backup time is similar. It's 56 versus 52 minutes. Well, give or take, doesn't matter much. But restoration, wow, it's like 57 minutes versus 325 minutes of logical time. So the growth of logical restoration time correlates with heavily, linearly, almost linearly with the size of the data that you have. And but the time that it takes to back up and restore with physical capability is not changing. It's almost flat, right? Definitely, once you have more and more data, you need to face networking issues, you need to face or limits, and you need to face disk limitations, like how many IOPS you can write and read. But it's not that of a dramatic change, right? Because 325 minutes versus 57 minutes is almost like 6 times, right, difference, which is definitely a lot. So these are the results. And now let's look into the details, what's happening underneath. So physical backup tech peek. I'm going to go pretty deep into the technical implementation of physical backups in Percona Backup for MongoDB. I will talk about the internal functions that we use in MongoDB to address some of the consistency issues and so on. And I will also provide some good blog posts that you can read so that you would understand what's happening in more details within PBM and within MongoDB when we take the physical backup and when we restore the data, obviously. So let's start. So the question is, what do you need for physical backup? The answer is extremely simple. You need the list of files to copy to some storage. But at the same time, the critical aspect here is that you need to ensure cluster-wide consistency, which means, okay, you can copy the data from some random node in replica set, but how do you know that it is the latest data? How do you know that once you restore this data, that it is going to be what you really expect, that it is consistent with what you're expecting, right? So these are crucial items, and PBM is addressing this cluster-wide consistency problem. So let's see how we do that. So first of all, what we do first is we need to get the files. How do we get the files? Is we use backup cursor. Backup cursor was introduced in Percona server for MongoDB, this version 4.4.6, and it is the function, right? But it's not the function that you would use to query your data. It's the function for DBAs, and everything in White Tiger is a cursor, like the same way everything in Linux or Unix system is a file. In White Tiger, everything is a cursor. So what does backup cursor does? It just returns the list of files that you need to back up. So you just say, hey, my MongoDB node, please tell me what files do I need to back up to perform a physical backup. And backup cursor does this exactly. But not only that, it also returns some timestamp. We'll talk about it a bit later on the next slide, but keep that in mind. And this is an important note here, that PBM physical backups work with PSMDB only, Percona server for MongoDB. The reason for that is backup cursor is the functionality that was implemented in Percona. And what we are trying to do, we're trying to implement the same APIs and the same functions that you have in MongoDB Enterprise. And as you know, MongoDB Enterprise is closed source. What they have in community version, we use it, but on top of it, we build some enterprise grade functionality, which we open source later on. The same goes with backup cursor. Backup cursor is not available in MongoDB community version, so we had to re-implement it. We had to come up with our own solution for that. But we're trying to implement it in a way that it is compatible with MongoDB Enterprise, but we cannot guarantee its compatibility. So when I say PBM physical backups work with PSMDB only, maybe it's not. Maybe it would work with enterprise version of MongoDB, but we cannot just guarantee it, because some implementations might be a bit different and we cannot guarantee it. So if you're going to use PBM physical backups, please use it with Percona server for MongoDB. So this is backup cursor example. Let's see what is happening here. There are two important things that I want you to look at. First one is this backup ID. We'll need to use it later on, but it's fine. Another one is this one, important one, oplog end. This is the timestamp which indicates the latest transaction written on this specific node where you run this command, right? Aggregate backup cursor. So this is, again, this is the timestamp on this node that indicates the latest transaction written or the latest data written on this node, the latest oplog produced, right? And then we have the list of files. So it's white tiger files with the full path to them. These are the files that we are going to upload to our storage as a backup. But first, we need to ensure consistency. And to do that, we need to understand what is the latest time that we can use for our backups, right? And this is this oplog end time. This is the timestamp that we use. And in backup cursor, once you query, it returns this the list of files, and we get this timestamp once we execute this command. And we do it on all the replica set nodes. And the latest timestamp, so the latest time that we see, the biggest one, is the one that we're going to use as our backup and recovery timestamp. We're going to call it common backup timestamp. So it's common across all the nodes. And here again, you see it. I put it here as an example again, oplog end. This is the timestamp that we're going to use for our backup. So all the nodes on when we're going to take the backup on all the nodes, we're going to use this common backup timestamp as the time of a backup and the time of restoration. And how do we do that? We're going to use another function, which is called backup cursor extend. And what it does, it gets two parameters into it. It gets backup cursor ID, the one that we ran before, and it gets the timestamp. And once you ship these parameters to this function, backup cursor extend, it just waits till the node reaches this common backup timestamp. And once it reaches this timestamp, it just returns the list of journals since the cursor was opened. So now you have the list of files that you need to back up that backup cursor returned you. Now you have the timestamp that you agreed on that you are going to use across the cluster to take the backup. And now you have the list of journal files since backup cursor was opened. So you have all three components that you need. So you have the list of files, you agreed on the you agreed on the cluster-wide consistency time, and also you have this journal files since backup cursor, so you're sure that you will not miss any file during the backup process. So to make it simple, this is the example of executing backup cursor. So first you execute this backup cursor command. You get the list of files into the variable. Then you extract the metadata. And this metadata has backup cursor ID, and it has the timestamp of the last oplog. And then you execute backup cursor extend, and you provide it with backup cursor ID, backup ID, and you provide it with the timestamp as an input. And what you get is you get the white tiger log files. So you get these journal files. So now you can upload the backups, and now you can upload these files to your storage. So this is just an example of how it works under the hood. As you see, you can try it out with your MongoDB deployment and execute these commands and get some result. But what we do in PBM, we kind of automate it, so you don't need to interact with Mongo shell at all. So let's glue it all together, because I understand it might be a bit overwhelming. I will explain it in details once again. So what is happening is the first step. I believe I have not discussed that, but what is happening is that Percona Backup for MongoDB PBM chooses a backup leader in the replica set. So you have multiple replica set nodes, and I'm going to show one only here, but what is happening in PBM is picking one of the nodes in each of the replica set as a backup leader. We want to interact with one node only, so PBM agent is going to do all the work on one of the nodes in the replica set. We don't want to interact with other nodes because it doesn't make any sense. We're going to synchronize the data. So what is happening? We are opening backup cursor. So PBM says, hey, replica set node, open backup cursor. Backup cursor created. Now we get the list of files that we're going to back up, and we also get the metadata, which has the important information. It has backup ID, and it has the timestamp that we need to agree on. We choose the latest op log timestamp. So we chose it across all the nodes that we use. We chose the latest timestamp. And now we're going to open backup cursor extend or execute this command. We provide backup cursor ID and the timestamp. And what replica set node does, it returns us the journal files. And now what we do, what PBM does, it uploads files and journals to external storage. And that's it. Now we can close the cursor once the backup is done, once files are uploaded, and that is done. Right now we have files and journals on our storage, and we ensured consistency because we pick the common timestamp across all the nodes in our cluster, across all the shards, not all the nodes, but all the shards. And that's it. And it happens for each and every replica set in your cluster with the same common time. So that's it. Backup is done. Backup uploaded. Let's talk about the restoration process. Restoration process, I would say, is a bit easier, but it has its own quirks. So there are some problems. First one is sometimes it is possible that in your backup, once you upload all these files, there will be the data which is beyond your timestamp that you chose during the this conversation with replica set. It is possible that you will have some chunks of data that are beyond this common backup timestamp. This is problem number one. Problem number two is when we do the restore of the database, we need to shut it down because we cannot allow anyone writing to the database when we are restoring data on a physical disk, because that would corrupt it, that would do I don't know what, but we are shutting down the cluster. That's another problem, and I'll explain why this is a problem on the next slides. And another thing that we had to brainstorm a bit is, do we want to restore our data on only one node? So you have 3 nodes in the replica set, let's say. Do you want to restore your data on one node in this replica set and then synchronize it to all the nodes? Or do you want to restore your data on all the nodes, put it on all the nodes on the disks simultaneously, and just start up the database? So we had to think about it a bit, and we'll discuss it. And as I said before, on problem number 2, we are shutting down the cluster. So the cluster is down. Do we want to bring it up? Do we want to start up the cluster? Do we want to do all the heavy lifting with starting up Mongos and so on and so forth, or not? So these are the 4 problems that I want to discuss for restoration. So first one is super simple. So yes, we have some data which is beyond this common timestamp that we chose, but gladly there is a function to limit oplog. So once you restore the data, you can set some oplog truncate after point value. We set it in the local replica set database, and once you set this, then the restoration will not go any further. and that's it. But you just need to be aware that there might be some data which is beyond your point. That is how we address it. We just cut it. After this point, no data is going to be restored. Just keep this in mind. Communication with the database. So yeah, so we shut down the cluster because we don't want anyone to interact with the database when we're writing data to the physical disk. But the problem is that PBM agents, they communicate with each other. If you remember, I told you that before, they communicate with each other through MongoDB collection. So it is one of our components of PBM architecture. We have a collection in a MongoDB cluster through which PBM agents talk to each other. So, hey, I'm doing a backup, hey, I'm restoring, or whatever. And when we shut down the database, no communication is happening. So what should we do now? What we decided to do is that PBM agents are communicating through storage. We have a storage now where we have the backups and so on, and agents can communicate through storage as well when they restore. Why do we need this communication? For example, you need to check if data is restored. How do you know it? You don't know, right? So PBM agents, they need to talk to each other and verify, hey, PBM agent on node 1, have you restored it? Yes, I have. Have you restored it? No, not yet. I'm still uploading the files. Have you restored it? No. So they need to talk to each other and verify. And this communication is important because it would allow us to provide you with the information if the backup is done, if there are any errors, if something is going on during the restoration, because database is down physically, right? You cannot check it and you need to sit and wait. So PBM CLI can provide you this information, and it talks to PBM agents through the storage, which is pretty awesome. So this is one of the problems that we solved. And yeah, this is just the solution. It's not the problem anymore. So what we decided is we want to restore data on all nodes as it is much faster. So you have a replica set with 3 nodes, and you have PBM. And what we do, we take the data from the storage and we start putting it on the disks of each and every replica set node simultaneously. So we restore to all nodes simultaneously. And the reason why we do it, imagine if we would put data on only on one node. So node number 1, we put it there, we start MongoDB process, we create the replica set, we format and so on. What would happen next is that MongoDB would start the replication process. And imagine if you have terabytes of data or petabytes, then it would take you again a lot of time to have your cluster up and running, to have your cluster ready. And instead of doing that, we decided to go with this simultaneous restoration so that it is much faster. Once you're done with restore, the data is similar on all the nodes. You just fire up MongoDB and your replica set is up and running, and data is synchronized across all the nodes. That's one of the decisions that we made. And another decision here is we want users to bring up the cluster after the restore. So the user executes the command PBM restore, it shut down, it kills the cluster, it starts, wipes the data on the disks, right? It starts uploading the data from the S3 bucket or from something else to the disk. And once it is done, PBM agents can report to PBM CLI that the backup is there, that it's finalized. But we do not want to go into this story where we need to start the replica set nodes or MongoDB processes, that we need to verify if they are up and running, if that we need to go to the balancer, to Mongos and start them as well. So it's a lot of work, and there are a lot of questions that we need to address if we want to go that road. And we just don't want to do that because it is much, much simpler for the user to do that. And also what we are going to do, we're going to automate it with some of our tools. Like we have Percona Operator for MongoDB. It is our Kubernetes solution to run our MongoDB distribution and PVM on Kubernetes. And we already have this backup and restore automation in the operator for logical backups. What we are going to do, we're going to introduce physical backups and restoration automation as well there. So operator is going to do all the heavy lifting of spinning, stopping the nodes, studying the nodes, because there are multiple restarts that are happening during the restore process. It's well described in the blog post. I'll share it on the next slide. So feel free to read it through. It's very interesting. Our tech team, engineering team wrote this blog post specifically about physical backups in MongoDB, and it talks about how restoration is complex. Yeah, and another thing is we're going also to provide the automation in Percona monitoring and management. It is our solution for observability and database monitoring and management. And one of the capabilities that we have there is managed backups. For now, it's again only logical, but we're going to introduce physical backups there. And once you click a button, backup and restore, it's going to do all the heavy lifting for you, so you would not need to do it manually. But for now, if you're using PVM, you'll need to restore the data and start up the cluster manually. I think it's not a big step because restoration is not that common task, specifically for physical backups where you need to restore like terabytes or petabytes of data. So yeah, that's it. So we covered backups, we covered restores, we talked about the problems with restoration, we talked about the technical details of backups, and these are some links that I encourage you to look through and read. So first one is our GitHub repo. Remember, we are 100% open source. Another link is for our documentation, and there are 2 blog posts, backup, cursor extend, and Percona server for MongoDB. This is the very technical, detailed blog post about the internals of Percona server for MongoDB and how we implemented this backup cursor functionality so that to enable this physical backups in PVM. And the second blog post was written by our engineering team about physical backups in Percona Backup for MongoDB. It has lots of technical details as well, how it works, what is happening under the hood. So yeah, I encourage you to look through these links and please let me know if there is anything. Yeah, so this is the last slide. I really appreciate your time. Thank you all for joining. And if you have any questions, please ask them through email, through Twitter, or you can also reach us out on our community forums or Jira, for example, if you want to submit a bug. So thank you, everyone. I appreciate your time. Have a good day.